Hello friends. So today we will be seeing about NumPy and we'll be doing some examples and exercises based on NumPy. And first of all we'll be seeing what is NumPy, it, how it is better than other built-in functions and all. So let's begin. First of all, what is NumPy? NumPy is a fundamental package for scientific computing in Python. It is a Python library that provides a multidimensional array object, various derived objects such as masked arrays and matrices, and an assortment of routines for fast operations on arrays, including mathematical, logical, shape manipulation, sorting, selecting, input output, discrete Fourier transforms, basic linear algebra, basic statistical operations, random simulation, and much more. So, from this paragraph, we are getting that NumPy is nothing but uh, a package, built-in package for doing complex mathematical functions, and machine learning involves nothing but big data sets of uh, matrices, big data sets of numbers basically. So it involves many complex applications on metrics, and also NumPy is basically suitable for them. Now, what is a matrix? A matrix is a collection of numbers arranged into a fixed number of rows and columns. Usually, the numbers are real numbers. In general, matrices can contain complex numbers. In machine learning, we perform various matrix operations. Data is stored in the form of a matrix. NumPy is used to solve complex matrix operations efficiently. So, on the right here, we can see image of a matrix, and on the right of it we can see the matrix multiplication operation, an example of matrix multiplication operation. Okay, so now in NumPy there is a method called vectorization, and because of vectorization NumPy is used in machine learning. So what is vectorization and why is it used in machine learning, and why is it so useful for machine learning operations? So vectorization is used to speed up the Python code without using loop, like for loops, while loops, etc. Using such a function can help in minimizing the running time of code efficiently. Various operations are being performed over vectors such as dot product of vectors, which are also known as scalar product, as it produces single output outer products which results in square matrix in dimension equal to length x of the product of the vectors. Element wise multiplication, which produces which product products the element of same indexes and dimension of the matrix remain unchanged. Vectorization can be efficiently done using NumPy. So why will be using NumPy? In short, because calculations are fast. Because of vectorization, there are it is a pre-built library, so less chances of errors, more efficient than other libraries like math, etc. We'll be seeing it later. Less code is needed while coding through NumPy, and broadcasting is available in NumPy. So without wasting much of our time, we'll be starting with the exercises. Okay, so first of all we will be going in the command prompt and opening our Jupyter notebook. Okay, so the Jupyter notebook has been opened, and the file has been saved in desktop. NumPy. Okay, so this is a Jupyter notebook file containing of exercises for learning NumPy. Okay, yes, so Python basics with NumPy. So welcome to your first assignment. This exercise give you a brief introduction to Python. Even if you have used Python before, this will help familiarize with you with functions we'll need for our later course. So some instructions are there before getting into the exercise. You will be using Python 3 for this exercise. Avoid using for loops and while loops unless you are explicitly told to do so. After coding your function, run the cell right below it to check your result is correct. After this assignment, you will be able to use Jupyter Notebooks. You will be able to use NumPy functions and NumPy matrix or vector multiplic operations. Understand the concept of broadcasting and be able to vectorize your code. So let's get started. So what are basically Jupyter Notebooks? We had discussed before also, but uh, we'll discuss a brief summary of Jupyter Notebooks. So Jupyter Notebooks are interactive coding environments. You will be using Jupyter Notebooks here. You only need to write code between the start code year and end code year comments. After writing your code, you can run the cell by either pressing shift plus enter or by clicking run cell, denoted by a play symbol in the upper bar of the notebook here. We will often specify X lines of code in the comments to tell you about how much code you will need to write. It is just a rough estimate, so don't feel bad if your code is longer or shorter. So let's start with our first exercise. So the first exercise is set test to hello world in the cell below to print hello world and run the two cells below. Okay, so we'll begin with the test. Remove the none and hello world. Okay, we'll run it. Shift plus enter. So yeah, we've got hello world. So it is matching with our the expected output. So yes, we are correct. Now, before moving ahead, what do you need to remember? You need to remember that while running your cells, use shift plus enter or run cell here, the run cell. Write code in the designated areas using Python 3 only. Do not modify the code outside of the designated areas. Okay, so let's get ahead with it. So now we will see building basic functions with NumPy. NumPy is the main package for scientific computing in Python. It is maintained by a large community. You can visit the community at www.numpy.org. In this exercise, you will learn several key NumPy functions such as np.exp, np.log, np.reshape. You will need to know how to use these functions for future assignments. Okay. So first we'll see about sigmoid function and np.exp. np.exp is nothing but it is used to calculate exponential of a given number or a matrix. So before using np.exp, you will be using math.exp to implement the sigmoid function. You will then see why np.exp is preferable than math.exp. So we'll begin with the exercise, and the exercise consists of build a function that returns the sigmoid of a real number x. Use math.exp x for the exponential function. So there is a reminder. So sigmoid of x, the formula for sigmoid of x is equal to 1 upon 1 plus exponential of minus x, and it is sometimes also known as the logistic function. It is a non-linear function used not only in machine learning, that's machine learning basically in logistic regression, but also in deep learning. And so here is the graph of sigmoid of x function. Sigmoid of x, the range of sigmoid of x is from 0 to 1. Okay. So let's get uh, to refer to a function belonging to a specific package. You could call it using package name dot function. Okay. So run the code below to see an example with math.exp. Okay. So import math, define basic sigmoid of x. This is a function we are making. So here x will be nothing but, so here your you will have to modify the code because start code here and end code here is given. So basically one line of code it is required. So s will be nothing but 1 in, upon element wise 1 plus np.exp. I think here we'll be using math.exp, right? Math.exp of minus x. So we'll run the code, shift plus enter, shift plus enter. Okay, so we have got the output similar to the expected output. So our output is right. But there is a note that actually we rarely use the math library in deep learning because the inputs of the functions are real numbers. In machine learning or deep learning, we mostly use matrices and vectors. This is why NumPy is more useful. So we'll see an example why math.exp is NumPy is useful than math.exp basically. So here is an example. First, an a vector is created. X is equal to 1 comma 2 comma 3. There it consists of three numbers. Applying our previous basic sigmoid x function that we have created here, calling our basic sigmoid x function and running it to the vector, we get an error. So basically math.exp does not support vectors, and machine learning consists a lot of vectors, matrices, etc., etc. So to solve the problem related to vectors and matrices, np.exp or numpy is more useful than math function. Okay, so we'll move ahead. In fact, if x is equal to x1, x2, comma xn is a row vector, then np.exp x will apply the exponential function to every element of x. The output will thus be np.exp of x is equal to e raised to x1, e raised to x2 till e raised to xn. So now we will see with numpy the result. Okay, what numpy. Okay, import numpy as np. Now it is the program is written previously, so we just have to run it and see the result. Okay, so shift plus enter. So we have got the result 2.718, 7.38 and 20.08. Okay, furthermore, if x is a vector, then a Python operation such as s is equal to x plus 3 or s is equal to 1 by x will output s as a vector of the same size as x. So now we'll run the next code to see, to visualize the statement. Okay, so basically now we understand that through numpy we can perform operations on vectors and matrices also, right? Now we'll move ahead. There is a note, and anytime you need more info on a numpy function, we encourage you to look at the official document of this is the link provided. You can just click on the link, so you will be directed to the official document of numpy. You can also create a new cell in the notebook and write np.exp question mark to get quick access to the documentation of numpy. Now there is an exercise. Implement the sigmoid function using numpy. So instructions are given as x could now be either a real number, a vector, or a matrix. The data structures we used in numpy to represent these shapes, vectors, matrices, are called numpy arrays. You don't need to know more for now. Okay. So for x belongs to r raised to n, like n dimensional vector, sigmoid of x is equal to sigmoid x1 x2 up to xn, and after applying the sigmoid function, the matrix becomes, or the vector becomes, 1 upon 1 plus e raised to minus x1, 1 upon 1 plus exponential of minus x2 till 1 upon 1 plus exponential of minus xn. So we'll be doing the exercise. First we'll be importing numpy, import numpy as np. Then we'll begin our sigmoid function. Define sigmoid of x is the input variable, and now we have to write our code here. S is equal to sigmoid of, we have to calculate here the sigmoid. So s is equal to 1 upon 1 plus np dot exp of minus x. And now we'll run it. Shift plus enter, shift plus enter. Okay. Okay, so now we have got our output as 0 0.7, 0 0.88, and 0 0.95, and it is matching with the expected output, so our output is correct. Now we'll see about sigmoid gradient. You will need to compute gradients to optimize loss function using backpropagation. Let's code our first gradient function. So the exercise is as mentioned. Implement the function sigmoid underscore grad to compute the gradient of the sigmoid function with respect to its input x. The formula is sigmoid underscore derivative of x is equal to derivative of sigmoid function we have computed before, and that can also be written as sigmoid of x into 1 minus sigmoid of x. Formula is provided, and you often code this function in two steps. Set s to be the sigmoid of x. You might find your sigmoid of x function useful. Compute sigmoid derivative of sigmoid function is equal to s into 1 minus s. So s we have computed before. All right. Okay. So we will the same formula will be applied, or we will call the function from previous function sigmoid of x. Okay. And then ds is equal to s into 1 minus as the formula is given right here. So s into 1 minus s. Okay, and then we'll run our code. So our output is 0 0.19, 0 0.104, and 0.04, and yes, it is matching with the expected output, so our code was correct. Now we'll see about reshaping arrays. So two common NumPy functions used in deep learning are np.shape and np.reshape. X.shape is used to get the shape or dimension of a matrix or vector x. X.reshape is used to reshape x into some other dimension. For example, in computer science, an image is represented by a 3D array of shape, length, height, comma depth is equal to 3. However, when you read an image as the input of an algorithm, you converted it to a vector of shape length into height into length by height by 3 comma 1. In other words, you unroll or reshape the 3D array into a 1D vector. So don't worry if you are not understanding this concept. When you will do the exercise by yourself, you will be understanding it. So we'll be doing this exercise will is as given. Implement image to vector. The function is given below, that takes an input of shape length comma height comma 3 and returns a vector of shape length by height by 3 comma 1. For example, if you would like to reshape an array v of shape a comma b comma c into a vector of shape a comma a by b comma c, you would do v is equal to v dot reshape v dot shape 0 into v dot shape 1 comma v dot shape 2. Okay, so please don't hardcode the dimension. Note is given, please don't hardcode the dimensions of image as a constant. Instead look up the quantities you will need with image dot shape 0 etc. Okay, so we will be doing the below exercise given below. So here we started. So we will be nothing. Okay, we will be taking some idea from the given formula above, and we'll be writing it. So we will be nothing but image dot reshape. Sorry, image. I'm wrong. Np dot reshape. Uh, 1 minute. Yes. So it will be image dot reshape. Um, image dot shape 0. Okay, so here basically 0 and 1 denotes x-axis and the y-axis. So we'll be taking 0 means x image dot shape 0 means x-axis, and into image dot shape 1 means the y-axis of the matrix, into image dot shape comma 1. Okay, so our code is done and we'll run it. So the output of our code is, it is a vector of 0.067, 0.029 and so on. And is it matching with the expected output? Yes, 0.67, and the last last value is 0.946, and yes, so it is matching with the expected output, so our code was correct. Now we will see normalizing the rows. Okay, another common technique we use in machine learning and deep learning is to normalize our data. It often leads to a better performance because gradient descent converges faster after normalization. Here by normalization we mean changing x to x upon norm of x, dividing each row vector by x of x by its norm. For example, if x is equal to a matrix of 2 by 3 dimension, 0 3 4 2 6 4, then x will be np dot lionel dot norm. This is the formula, you have to mug it up. np dot lionel dot for normalization, it is the formula used. x comma x is equal to 1, keep dims is equal to true, and this keep dims is equal to true is used to keep the dimensions uh, as constant. So it is like we have to use it in the formula as a default value, and the output give is 5 upon 5 and root 56. Okay, and x normalized is equal to x upon norm of x is equal to 0 upon 2 by root 56, 3 0, 3 by 5, 4 by 5, 2 by root 56, 6 by root 56, and 4 by root 56. Note that you can divide matrices of different sizes and it works fine. This is called broadcasting, and you're going to learn about it in part 5 of this assignment. So exercises is given. Implement normalize rows function to normalize the rows of a matrix. After applying this function to an input matrix X, each row of X should be a vector of unit length, meaning length 1. Okay, so will the function has been created for you. Now you have to apply the X norm formula and then calculate X. Okay, so we'll be doing it. X norm is nothing but the formula. By using the formula given above, we will use x upon np dot linel dot norm x comma x is equal to 1 comma okay, so x is equal to x. So it is done, and we'll run it. So our output is a matrix of 2 by 3 dimension, and the values are 0, 0.6, 0.8, 0.13, 0.82, and 0.54. And yes, it is matching with the expected output, so our code was correct. And there is a note given. In normalized rows, you can try to print the shapes of x norm and x, and then rerun the assessment. You will find out that they have different shapes. This is normal given that x norm takes the norm of each row of x. So x norm has this same number of rows but only one column. So how did it work when you have divided x by x norm? So this is called broadcasting, and we'll talk about it now. So broadcasting is an important concept, mm, and it's useful for later courses. Broadcasting and the softmax function. A very important concept to understand in NumPy is broadcasting. It is very useful for performing mathematical operations between arrays of different shapes. For the full details on broadcasting, you can read the official broadcasting documentation. The link is provided. You can just click on it. And now we will be doing the exercise. Implement of softmax function using NumPy. You can think of softmax as a normalizing function used when your algorithm needs to classify two or more classes. Okay, so instructions is as given below. X is a matrix of 1 by n dimension, and softmax of x is equal to softmax of x1 x2 till up to xn is nothing but exponential of x1 upon summation of exponential of xj, and exponential of x2 upon summation of exponential of xj up to exponential of xn upon summation of exponential of xj. Okay, so we'll be implementing the softmax function by the formula and instructions given here. Kindly read the instruction. Okay, and a note is given. We'll just read the note. Note that later you'll see m used to represent the number of training examples, and each training example is in its own column of the matrix. Also, each feature will be in its own row. Each row has data for the same feature. So softmax should be performed for all features of each training example. So softmax would be performed on the columns once we switch to that representation later in this course. However, in this coding practice, we are just focusing on getting familiar with Python. So we are using the common math notation m by n, where m is the number of rows and n is the number of columns. Okay, so we'll be doing the exercises. So softmax function has been created, and we have to apply the formula in the function. So right here, the by applying the above instructions and formula, we'll be having np dot exp of x. Apply exp element wise to x. We have applied, and here create a vector x sum that sums each row of x underscore exp. Use np dot sum. Okay, so we'll be using np dot sum formula here. X underscore exp, x is equal 1 and keep them equals true. Okay, done. And s is equal to x underscore exponential upon x underscore sum. And our softmax function is done. Okay, so we'll run it, and the output is for the array 925007500 as input array, and applying the softmax function to it, we get the output as 9.808, 8.944, 1. These are big values, and just we'll match it with the expected output. And yes, it is matching with our expected output. So yes, our code was correct, and we'll be moving on to the next exercise. Note, if you print the shapes of x underscore exponential, x underscore sum, and s above, and rerun the assessment cell, you will see that x underscore sum is of shape 2 comma 1, while x underscore exponential and s are of shape 2 comma 5. X underscore exponential upon x underscore sum works due to Python broadcasting. So congratulations, now you have a pretty good understanding of Python NumPy and have implemented a few useful functions that you will be using in deep learning or machine learning. Now what you need to remember from these exercises. np.ex exponential of x works for any np.array x and applies the exponential function to every coordinate. The sigmoid function and its gradient. Image to vector is commonly used in deep learning and machine learning. np.reshape is widely used. In the future, you will see that keeping your matrix or vector dimensions straight will go toward eliminating a lot of errors and bugs. NumPy has efficient built-in functions, and broadcasting is extremely useful. Now we'll see about vectorization, and it is also a very useful topic. And we use NumPy because of vectorization. In deep learning and machine learning, you deal with very large data sets. Hence, a non-computationally optimal function can become a huge bottleneck in your algorithm and can result in a model that takes ages to run. To make sure that your code is computationally efficient, you will use vectorization. For example, try to tell the difference between the following implementations of the dot or outer or element-wise product. The code is previously been coded for you, and you just have to run and see the difference between vectorization on and non-vectorized implementation. So, um, one minute. So after running the this cell and this cell, the first cell was unvectorized implementation, the classic dot product implementation, and the second one was vectorized implementation. So we can see that the time for vectorized implementation is much lesser than dot product implementation. So we get that vectorized implementation is much more efficient and less time consuming that than the classic dot product implementation or loop implementation. We can say for loop and while loops we use. Okay, so avoid for loops and while loops while doing machine learning problems. Use vectorization as much as you can. And so here is a note. As you may have noticed, the vectorized implementation is much cleaner and more efficient. For bigger vectors or matrices, the differences in running time become even bigger. Note that np.dot performs a matrix or matrix vector multiplication. This is different from np.multiply. And the star operator, which is equivalent to element-wise multiplication in MATLAB or Octave, which performs an element-wise multiplication. So the last exercise we'll be doing is implementing the L1 and L2 loss functions. And the exercise is implement the NumPy vectorized version of the L1 loss. You may find the function absolute value of x useful for this exercise. And a reminder, the loss is used to evaluate the performance of your model. The bigger your loss is, the more different your predictions are from the true values. In deep learning, you use optimization algorithms like gradient descent to train your model and to minimize the cost. So L1 loss is defined as L1 and the inputs are y hat comma y. Y hat is nothing but the predicted value, and the y is actual value or true label we can say. And the formula for it is summation of I is summation of yi comma y hat I from I is equal to 1 till m. So we'll be implementing numpy to calculate it. Define L1 y hat comma y. So here we'll be using the loss function for np dot product implementation by numpy. And we'll run it. Sorry, some error is there. Y hat. Oh, sorry. Oh, so okay, there is a correction. The expected output should be 0.43 rather than 1.1. So our previous output was correct, and so our code is right. And there is a last exercise based on it. We will implement L2 here. Implement the NumPy vectorized version of L2 loss. There are several ways of implementing the L2 loss, but you may find the function np dot dot useful as a reminder. If x is equal to x1, x2, xn, then np dot dot x comma x is equal to summation of j is equal to 0 to n xj, um, xj square. Okay, so please note that in the previous exercise it was loss is equal to np dot sum absolute of y minus y hat, and then the output comes to 1.1. Okay, and then in this exercise implement the numpy vectorized version of the L2 loss. There are several ways of implementing the L2 loss, but you may find the function np dot dot useful. As a reminder, x is equal to x1, x2 up to xn, then np dot dot x comma x is equal to summation of j is equal to 0 to n xj square. So L2 loss is defined as L2 y hat comma y is equal to summation of I is equal to 0 up to m y I y1 comma minus y hat I squared. So we'll implement it using numpy. So np dot dot y minus y hat. Okay. Okay, so now the output is 0.43 and it is matching. Congratulations, you have completed this assignment. And now we'll be ending our session and hope you liked it. Thank you.